Here are some practice questions on acids and bases. Question number 1 wants to know which of the following statements are true concerning acidic solutions. And you have to kind of read them carefully. A solution with a pH of 3 will always indicate a strong acid. And if the pH is 5, it's always a weak acid. And although you may have been told that, it's not always true. pH is a measure of the amount of hydrogen in the solution. It's the opposite log of the hydrogen concentration. It doesn't matter where the hydrogen comes from. Now, obviously, if I have a solution of a pH 3, I could say that the hydrogen concentration is 10 to the negative third molar. And if the pH is 5, the hydrogen concentration is 10 to the negative fifth molar. And I could obviously tell you that if the solution has a pH of 3, there's more hydrogen because these are negative exponents of 10. So yeah, 10 to the negative third is greater than 10 to the negative fifth, but I don't know where that came from. What if I had a weak acid, but the molarity was really high? And so even though it doesn't ionize completely, if it was super concentrated, I could maybe still get 10 to the negative third moles of hydrogen out of what's technically a weak acid. The strong weak thing is just about their tendency to ionize, a percent ionization or a Ka value. A solution with a Ka, speaking of Kas, 10 to the negative second will always be a stronger acid than 10 to the negative sixth. That's a yes. If the Ka is larger, there's always more ions produced in solution, and that would always represent an acid that is stronger. The above statements are not all true. And then the last one, a 10 molar solution will always be more acidic than a 1 molar solution. We kind of have to take all factors into consideration. What if it's a 10 molar solution of a weak acid? And so I'd really have to know then, well, what percent of the weak acid does dissociate? So like of that 10 molar solution, how much hydrogen do I really get? I could have a 1 molar solution, so the concentration is less, but it's a strong acid, and it 100% fully ionizes to give me 1 mole of hydrogen. That might still be more acidic than a 10 molar weak acid solution that maybe doesn't ionize by much. So really the best ways of judging strong and weak are either by looking at percent ionization or Ka values. Number 2, what is the concentration of hydronium, H3O+, when the hydroxide concentration is 10 to the negative fourth? And there's a whole bunch of equations in your packet in the equilibrium section, and most of them are acid-base. Hydrogen times hydroxide is always 10 to the negative 14th, so I can just plug it in and solve for the hydrogen concentration, which, by the way, this is how they show the equation in the packet. Hydrogen and hydronium, I mean, these guys really, like, quantitatively mean the same thing. It's just that in reality, if I am producing positive hydrogen ions in a solution, they're probably going to be attracted to that negative oxygen of a water molecule. So you might see it written either way, but numerically it means the same amount of hydrogen in the solution. 10 to the negative fourth moles per liter. Number 3, the conjugate base of the bicarbonate ion. Okay, so that HCO3 minus, if it's in solution, it does have a hydrogen in there, so it could donate the hydrogen. It would probably be picked up by that negative oxygen of the water molecule. Well, in this case, the acid is the hydrogen donor, so that bicarbonate ion could act like an acid and donate the hydrogen. Water would act like a base. Water would be the hydrogen acceptor. Conjugates are the charged particles on the product side. It's like asking ourselves, well, what if this thing has to shift in reverse? What if it goes in reverse? Well, then what's got to happen? Well, obviously then that H3O+, he's got the extra hydrogen, but he'd have to give it back. So if he donates the hydrogen, he'll act like an acid, but we call it the conjugate acid on the product side, and it would be picked up by the negative ion, the conjugate base. So that carbonate -2 ion would act like a base. On the product side, the conjugate acid is usually the positive ion because it's positive due to that extra hydrogen ion. And the negative is usually your conjugate base. It could be attracted to hydrogen and shift this thing in reverse. So bases are often negative ions and acids are often positive. Number 4 wants me to rank the following bases. Which of the following is the weakest? Well, they've given me acids. They've given me a bunch of acids that have Ka values. They also start with hydrogen, so I probably would have guessed that they were acids. Now, if it would have said something like rank these acids, I would say, oh, piece of cake. I'm just going to rank them from smallest to highest Ka value. The smallest Ka is that HCN, so that would be the weakest acid, the one that really doesn't go forward and make a whole lot of ion. And the strongest acid is the HClO3. And in fact, we even say that one is a strong acid. Its Ka is greater than 1. The others would be weak acids with pretty small Ka values. So ranking these by acid strength would be no big deal. That'd be super easy. And for the most part, ranking them as bases isn't bad either. It's kind of the opposite. I would say like the reason why this HCN is the weakest acid well, it's really because this negative cyanide ion. That cyanide ion is really attracted to the hydrogen. If he's so attracted to the hydrogen and it just doesn't let go and dissociate, well, yeah, that's a weak acid. Obviously, it could produce some hydrogen, but because that cyanide has such a strong hold on the hydrogen, it doesn't dissociate much. Well, that's the definition of a good base. A base is supposed to be a particle that is attracted to hydrogen. So the negative conjugate base of a weak acid is actually a pretty good base. On the flip side, we said that HClO3 is actually a strong acid. I mean, it's the strongest of these, but I'd also just rank that as a strong acid. It's got a high Ka value. It's greater than 1. Well, a strong acid dissociates fully. Yeah, it must mean then that this chlorate ion is not really attracted to his hydrogen. They split apart really easily. And the definition of a good base is a particle that's supposed to attract hydrogen, react with hydrogen, remove hydrogen from the solution. Chlorine, not so good at that. The chlorine, the chlorate ion, they split apart from the hydrogen almost immediately. I mean, that's why it's a strong acid, but then on the flip side, it makes for a pretty weak conjugate base. And so it's a mouthful, but we'd say the negative conjugate base, so the negative ion from a strong acid, is actually a really weak base. It's the weakest bases. It's even weaker than water. But the negative ion from a weak acid is actually a pretty decent base. Those are stronger bases. Now, if you wanted to confirm this, you could also do that little calculation, Kw equals Ka times Kb. You could take Kw in the packet, which is 10 to the negative 14th. You got the Kas, then you could go ahead and solve them all for Kb, and you could rank them that way too to see which one has the highest or the lowest Kb. Or in this case, you could kind of just think, well, it's the opposite of the strength of the acids. Question 5. I want to know which of the following is true of this weak acid. Hypochlorous acid is weak because its Ka is tiny. Now, you maybe don't even need to set up the full ice table, but in solution, which would mean that water is present, that weak acid would be the hydrogen donor. I would form his conjugate acid and conjugate base, the negative ion and the positive H3O plus. I've got this 1 molar solution, but I know that if it's a weak acid, it's not going forward 100%. So in the end, the concentration of the hydrogen ion is going to be a lot less than 1. Same to be said about the ClO minus, the hypochlorite. Whatever it is, it's going to be a lot smaller than 1. I mean, they won't be 0. There will be some ions produced. They will never be greater than 1. And it would only be equal to 1 if it was a strong acid that totally ionized 100%. 6 and 7 kind of refer to temperatures of water. Kw is temperature dependent, as are all equilibrium constants. There's always some kind of an energy component to a chemical reaction. We don't always write it in the equation, but they're either endothermic or exothermic, and here that's kind of what we're trying to determine. So I do notice that as I'm increasing the temperature, the Kw is getting larger. Kw, they tell you in the packet, Kw is a product of those two ion concentrations. It's the hydronium and the hydroxide. But if Kw is increasing at higher temperatures, it must mean that this is shifting more forward at higher temperatures, that these concentrations are increasing. That's how my Kw gets larger. Okay, so increasing the temperature is making this thing shift more forward. Well, Le Chatelier would say that increasing the temperature is like adding energy, and you would shift away from what was added. So energy must be on the reactant side. So that if I'm adding energy, I'm shifting away from energy, which would be in the forward direction. The self-ionization of water is an endothermic process, just meaning that water on its own tends to ionize. Now, sometimes we write it like this, or sometimes we might just write it as like H2O can split apart to form hydrogen and hydroxide. It's just that in reality, when there are hydrogen ions in water, the oxygen of the water molecule is probably going to pick up those hydrogen ions, and it would really exist as H3O+. But again, like quantitatively, same thing. So increasing the temperature increases Kw. We're shifting forward. This is an endothermic process. Number 7, using the chart above, calculate the hydrogen and hydroxide concentrations in a sample of water at 50 degrees. So I looked on my chart to find the K value. So at 50 degrees, the K value is 5.47 times 10 to the negative 14. Kw is only 10 to the negative 14th, I should say 1.0 times 10 to the negative 14th at 25 degrees. And they'll specifically say that in the packet. Often we just use Kw as 10 to the negative 14th, 1.0 times 10 to the negative 14th. Yep, but really only at 25 degrees Celsius, which is kind of close to like room temperature for water. But at 50 degrees, my Kw is different. But I know that it's going to still be a product of those ion concentrations. They're always going to be present at a 1-to-1 ratio, whether I'm shifting forward or reverse, if I increase or decrease the temperature. There'll always be a 1-to-1 ratio, so I'll just call them X, which then makes this calculation not so bad. Kw equals X squared. If I take the square root, both hydrogen and hydroxide are about 2.34 times 10 to the negative 7. Now, I think we also kind of mentioned, like, let's say they ask about pH. So if I said pH is opposite log of the hydrogen concentration, or hydronium, which is still this 2.34 times 10 to the negative 7 molar hydrogen or hydronium. If I plug that in my calculator, I get a pH of about 6.63. And so again, we said that often we are told water is neutral when its pH is 7. At 25 degrees Celsius. But when we change the temperature and we shift the equilibrium, we're going to form more or less hydrogen. In this case, when we're shifting more forward because we're increasing the temperature, we're going to get more hydrogen. Instead of 1 times 10 to the negative 7th moles of hydrogen, I've got like 2 times 10 to the negative 7th moles of hydrogen. So if I'm getting more hydrogen, then yeah, the pH is going to be less than 7. But what's key to also understand is that water is always neutral. Neutral doesn't necessarily mean the pH has to be 7. Neutral really just means that the hydrogen and hydroxide concentrations will always be the same. They're always on the same side of the equation. They're always at a 1-to-1 ratio, whether I'm shifting forward or reverse because I increased or decreased the temperature. These guys will always be the same. Water is always neutral, but the pH doesn't have to be 7. Number 8, I've got a weak base, hydroxylamine, and we want to calculate the Kb. All right, well, I just got to think then, like, what does a base do? So if I've got a solution of this weak base, it means that water is present. And a base is a particle that attracts hydrogen. It reacts with hydrogen. Well, the only source of hydrogen in this solution is now just going to be the water. So that base will remove a hydrogen from the water. This is going to be my base. Water is going to act like my acid. And so then on the product side, if this were to shift in reverse, I'd say, okay, well, the positive ion is my conjugate acid. With an extra hydrogen, he could shift this thing in reverse if he donated it back. And the conjugate base would be my negative ion, my hydroxide. So yeah, if they tell me it's a base, I know the job of a base is to react with hydrogen, remove hydrogen from the water that's remaining in the solution. And yeah, I can look at this equation and say that it's going to be a base because hydroxide is one of the products. When I write the Kb expression, I go products over reactants, but we do not include the liquid water. No pure solids or liquids. Number 9. I want to know which of these would be the weakest acid. They're all the same concentration, which doesn't really matter anyways. They all have the same Lewis structure. The only difference is they have a different halogen hanging off the end. And we say, okay, from the get-go, hydrogen is doomed. The hydrogen is hooked onto that highly electronegative oxygen. So already, the oxygen's going to pull electrons away from the hydrogen. But then oxygen calls for like a buddy to come on in and pull extra hard. So he's pulling in some of his buddies' halogens. And I've got chlorine versus bromine and iodine. And I look at the periodic table and I can see that they're all in the same group. And chlorine is the smallest atom. So the electrons are closest to the nucleus of its own atom, which creates a strong attraction and also a stronger attraction for neighboring electrons. Chlorine's got a higher electronegativity than iodine, so there's just like an extra pull on the electrons to be pulled away from the hydrogen in that HOCl. In the HOI, iodine's got a pretty low electronegativity, so it's like oxygen calls in a friend. It's like a 2 versus 1 tug of war, where I've got poor little hydrogen who doesn't stand a chance versus these two knuckleheads. Oxygen brought a friend, but he didn't bring a very good friend. If the goal was to help remove electrons from hydrogen, iodine's electronegativity is pretty small. Whereas here we've got a tug of war with hydrogen and 2 highly electronegative elements. So we're really going to pull away the electrons from hydrogen And if it makes that bond weaker between the hydrogen and oxygen, then it's easier to remove the hydrogen, and that actually makes it a stronger acid. So the weaker acid here is the one that's going to have a stronger bond between the hydrogen and oxygen. Now, they're all still acids, and oxygen is going to pull electrons away from hydrogen no matter what. But with iodine on the other end, there's just not as strong of a pull for the electrons to be drawn away from the hydrogen. So that bond should be the strongest of the three here, which means that it's going to be the hardest to remove the hydrogen. That's your weakest acid. 10 and 11. Pull out the calculator, set up some ice tables. Let's go. We've got the Ka for hypochlorous acid, and we want to know the pH of a 0.02 molar solution. And so sometimes people will say that the hardest part of these is writing an equation. And often you're given equations, especially in free response style questions, but even multiple choice, often give you the equation because they don't want you to get this wrong because you wrote the wrong equation. So the definition of an acid is a particle that donates hydrogen. Now, technically, if these are solutions, water is present. So water will pick up the hydrogen. I'll be left with the negative conjugate base and H3O+. I've got a 0.02 molar solution. I really never care about the water. I'm not going to use that in any of my calculations. Initially, those ions on the product side are 0, and we're going to shift her forward. We just don't know by how much to shift it. And we know X is going to increase on the product side. I have to have some ions. I can't have zeros at equilibrium. So we set up the ice table the best we can, and then we solve for X. But to make this a little more manageable, we say, well, I mean, that Ka is tiny. So X is also pretty small and maybe insignificant in the denominator. I've got 0.02 minus something really, really tiny. And realistically, like in the lab, we're only measuring maybe 2-3 decimal spots. Like maybe this is pretty insignificant. Now, obviously, you can't get rid of all the X's, but 0.02 minus X is probably pretty darn close just to 0.02. So you can get rid of that X in the denominator, cross multiply, take the square root, and then once I get X, if I want to solve for the pH, then X is the amount of hydrogen or hydronium. I can plug that in as opposite log of the hydrogen concentration, and bingo, I get a pH of 4.61. Bases are really, really similar. The equation's a little different just because a base is a particle that removes hydrogen. Now, this is also a solution, so water is present. Sorry, water, but that's where the hydrogen's going to come from. That negative oxygen on the end of this weak base. We'll remove a hydrogen from water. I'll be left with the conjugate acid, which is just the positive particle from that weak base, and hydroxide. Water is left as hydroxide when we remove a hydrogen ion. The ice tables look exactly the same then. We've got a 0.01 molar solution. I don't care about the water. My ions on the product side are 0 initially. It's got to shift forward because I can't have zeros at equilibrium. So we shift everybody forward by X. And really similar now when I solve for X, I mean, Kb is 10 to the negative 9th. So 0.01 minus something crazy tiny is probably insignificant. So we can ignore that minus X in the denominator, cross multiply and take the square root. This time when I'm trying to solve for pH and I know it's a base, I'm concerned with the amount of hydroxide in the solution. So I've got X, I've got the hydroxide, so I can do the POH, opposite log of the hydroxide concentration, Then when I get the pOH of 5.4, I say, oh, wait a second, bases have pHs that are greater than 7. We just got to subtract from 14. So pH plus pOH equals 14, and that equation would also be in your packet. Subtract from 14 and you get a pH of 8.6. So really, really similar ice tables. The main difference is just that when I've got a base, I got one extra step at the end. I'm going to get the pOH, and I have to subtract from 14 to turn it into a pH. 12 and 13, some more ice tables. 12. I got a 1 molar solution of some generic weak acid, and it's 1% ionized. Calculate the Ka. And so, yeah, often they give you the equations. So if that's what you're getting stumped on, I wouldn't lose sleep over it. A weak acid is just a hydrogen donor. And so, yeah, the definition of this acid is going to donate some hydrogen. It'll be picked up by the water. I'll be left with the conjugate base, the negative ion, and H3O+. I know the initial concentration. I don't care about the water. And initially, the ions are 0. But this time, instead of solving for x, we know that it dissociates by 1%. So we just take 1% of that original 1 molar solution, and x is 0.01. So we're going to bring the reactant acid down by 0.01 and the products up by 0.01. From there, we got everything we need to calculate the Ka. We'll go products over reactants. And again, I mean, you can use 0.99 in the denominator, but it's just going to be really tiny, and it almost doesn't even make a difference. The Ka ends up being about 10 to the negative 4. 13 is also kind of a cool ice table. If you want to calculate the Ka of an acid or the Kb of a base, you got to know the equilibrium line. You got to know like the concentrations of everything at equilibrium to calculate an equilibrium constant. So I got to be able to like fill out the ice table. I can't have X's in my ice table. Well, I could use a percent dissociation to know how far forward to shift it. But man, do people forget this. That if you know the pH, you know the hydrogen concentration. So we've got some weak acid, a 0.1 molar weak acid, and I just called it HX. I just kind of used the same generic acid as number 12. Monoprotic, just meaning that there's only one proton or one hydrogen ion produced in solution. So I use the exact same reaction, just some generic weak acid that'll produce one hydrogen that's picked up by the water. I'll form that negative conjugate base and the positive H3O+. But yeah, if they tell me the pH is 4, I know then that at equilibrium, the concentration of hydrogen is 10 to the negative 4th molar. And if I know the hydrogen is 10 to the negative 4th, or the hydronium, so is the conjugate base X minus. These guys would shift forward by X, or by a 1-to-1 ratio. I just already know what X is. At equilibrium, there's 10 to the negative 4th moles of hydrogen and X minus. Now, technically, that HX is going to go down by 10 to the negative 4th moles per liter. But again, it's super tiny. So I just stuck with 0.1 in the denominator. I mean, 0.1 minus 10 to the negative 4th, you can plug it in if you want to. But it's going to be really close to 0.1 in the denominator. I plug it in my calculator, products over reactants, and we get a Ka of 10 to the negative 7. And the last couple, I'm obsessed with number 14. This is adorable. They give me 3 acids. I've got their molarities and their pH values. And somehow I'm supposed to rank these from strongest to weakest. And I'm usually thinking, well, if I'm ranking strong, weak acids, I want a K value, right? I'm not supposed to look at molarity or pH. But we could kind of take both into consideration. If you take your calculator and you go opposite log 0.005, you really do get 2.3, which must mean that if this is a 0.005 molar of some acid, I am getting 0.005 moles of hydrogen. Now it's dilute, the concentration is small, but it's a strong acid. It must be totally ionized because that is the amount of hydrogen that would give me a pH of 2.3. So strong meaning that all of that 0.005 moles of acid dissociate to give me 0.005 moles of hydrogen. Well, then the other two, if those were strong, you should be able to go opposite log of 2, opposite log of 3. And, oh, wait a second. That is not 2.8. If I plug that in my calculator, I am not getting 2.8. Which must mean then that they are weak. So they are not giving me 2 moles or 3 moles of hydrogen. Even though they're more concentrated, they're not dissociating fully. I'm not getting that amount of hydrogen. And in fact, a pH of 2.8 means less hydrogen than a pH of 2.3. So yeah, they're like way more concentrated, but yet I'm getting less hydrogen. From acids Y and Z, those guys are weak. Now to decide between the two, I know that if they have the same pH, there's the same amount of hydrogen in the solution, 10 to the negative 2.8 moles of hydrogen. But Z had to be like even more concentrated in order to actually give me the same amount of hydrogen as solution Y. So for sure, X is the strongest and he would be strong. Y and Z are weak, but Z is the weakest with the least amount dissociated. And then finally 15 and 16. 15, salts. All right, so I don't know, people kind of get worried about these salt solutions, but check out a question like this. We've got NH3 with a Kb, that's small. That must be a base. And HCN with a small Ka value. It's a weak acid and a weak base. Well, I'm given some salts. So I noticed that the first one is sodium cyanide. I know in solution I would get sodium ions and cyanide ions, but I don't care about the sodium. The sodium is a spectator. The sodium is positive, but he's not positive because he's got like extra hydrogen to produce, so it's obviously not an acid. And with him being positive, he also can't act like a base. Sodium is neutral. But then the other ion in the solution is cyanide. And obviously it can't be an acid. Cyanide cannot be acidic because there's no hydrogen to produce. But he's negative. And we say, well, is he negative because he's like attracted to hydrogen? And the answer is actually, yeah. He's the negative conjugate base of this pretty weak acid. And those negative ions from weak acids can be pretty good bases. That's why they're weak acids. They're very attracted to hydrogen. They'll remove it from whatever source of hydrogen is present. If it's a solution of sodium cyanide, there's water present, and they'll say, well, fine, I'll take the hydrogen away from the water. And then bingo, look who's produced. Hydroxide. So yeah, if you've got the negative ion from a weak acid, that's your conjugate base. They're pretty good bases. The sodium is neutral, but the cyanide is a base. The second solution then is ammonium chloride. And that chlorine, neutral. And obviously it's not acidic, can't produce hydrogen. And even though it's negative and we think, well, I mean, wouldn't it be attracted to hydrogen? I know that HCl is a strong acid, which means that it's going to split apart right away anyways. So it's not really a great ion if you want to remove hydrogen from the solution. Chlorine is not a great base, but that NH3 ammonium is acidic. We ask ourselves, well, is this ion acidic because there's extra hydrogen? And the answer is obviously yeah. Yeah, there is. It's the conjugate acid of that NH3 ammonium. So in solution, he could give that hydrogen back to somebody like water. Water's got that negative oxygen in. Well, I don't take that hydrogen back. And bingo, look at one of the ions produced. H3O+. So yeah, if you've got a positive ion because it's got an extra hydrogen, that ion would act like an acid in solution. And finally, 16. Some acid-base Le Chatelier. Like, this is getting pretty sophisticated, but you got this. You can do this. The equilibrium reaction shown above represents the partial ionization of that weak acid. The Ka is super tiny, so it's not going forward by much. A 0.2 molar solution has a pH just around 5. If 0.05 grams of sodium cyanide are added to that solution, which of the following explains how and why the pH would change? Okay, so we're going to add some sodium cyanide. And we just said that sodium's a spectator. He's not doing anything. But then we've got cyanide. And so this is like the Le Chatelier's part of it. When you add something to an equilibrium system, you shift away from what was added. So we're adding more cyanide. We're going to shift in reverse. All right, so in shifting reverse, if they're asking me about the pH, I'm actually concerned with this H3O. pH is a measure of like how much H3O is in the solution, or hydrogen ions. But yeah, in shifting reverse, I'm going to also decrease the amount of H3O+. Oh, so if there's less hydrogen or hydronium, the solution would be less acidic. Less acidic meaning the pH is going to be higher than 4.95. It's that cyanide that'll disrupt the equilibrium, resulting in an increased production of HCN, which is a weak acid, so it's really not going to dissociate much. So I'm reducing the concentration of the H3O+ by shifting in reverse.